So we're talking about FlashBlade, and I'm going to take you through the foundation layer of how we've really simplified scalability for a lot of these modern unstructured data systems. The problem we wanted to solve here being scalability, well, let's unpack that a bit. What do we actually mean? Well, in a storage system, we say scale. It's sort of obvious we'd be talking about taking, from terabytes of data that we might have had in the last couple of decades to petabytes and even exabytes at this point. Like the capacity is pretty well understood that that's a big dimension of what we mean by scale. But in the unstructured world, we also need to talk about, well, how many files and objects do we support? And what we've seen in the industry is, as the changing of applications and the needs of modern data, we've gone from, order millions to we have customers in production that are hosting hundreds of billions of files and objects on one system. And so we have to meet that. We have to keep pushing the boundary of how, the metadata size and scale, but also how much compute gets attached. All this unstructured data has to be generated somewhere and it has to be analyzed somewhere. Otherwise, we're just sort of keeping it and not deriving value. And so we've gone from, 20 years ago, it might have been 100 cores or so of that scale in attached compute to this shared data to tens of thousands of cores of traditional compute plus GPUs, accelerators, and all sort of the modern compute infrastructure that's happening and all the applications that are driving that. And so that drives a need to really hit a high degree of scale. And if we do that, it poses a lot of problems. If we're going to meet these challenges, it poses a lot of problems for some traditional architectures and the way they've been built over the years. And we can, generically look at three existing approaches to sort of understand some of those issues. We have there was a big push 15 years ago to build direct attached storage clusters, commodity hardware. The sort of poster child of this was the Hadoop file system. And in its context and in its era, it achieved some really remarkable things. And in particular, it was optimized for data locality. And in an era of little slower networks, that can make a lot of sense. The problem in an era with really fast networks and more flexibility that's needed in sort of changing workload variations is it strands storage and compute capacity. And at the scale we're talking about, customers can't afford, the energy wastage is too high, the costs are too high to have stranded. We want every bit and every flop and every CPU cycle to be put to effective use. So stranding things is not okay. So if you look at the more classic storage approaches to this, you can say generically there's been a push to, in some cases, federate scale up storage arrays. And this has some good advantages, right? You can take a really feature-rich architecture that's been developed over the years and reuse a lot of those mechanisms and try to federate the namespace across multiple of those systems. But doing so often, at least what we hear from customers, is it leaves quite a few performance hotspots as it's difficult to manage balancing the data across these different, scale-up controller pairs, if you will. And the other kind of traditional storage-oriented approach or storage system-oriented approach is a traditional scale-out. And so these, we got to give credit where credit is due. There's some very large capacity storage systems that have been built and are running in production quite successfully, for large-scale content serving and archive. But what we find for a lot of modern data is that these architectures either limit the application performance due to just architecture that's chosen, spinning disk, trade-offs that were made at the time, or they expose really complex networking setups to hit this scale. Building multi-petabyte and up storage systems is a big challenge. And what we set out really from the beginning of FlashBlade was to try to build a simpler experience that still hits some of this scale. And one of the things we looked at closely was how networking works. And so if we look at any kind of scale-out networking architecture, scale-out storage system architecture, there are really three networks that are involved. There's a front-end network, client traffic comes in. There's a control network where nodes in the cluster have to communicate with each other to handle monitoring and management, health checking. This is actually very latency sensitive, high priority traffic, but very low bandwidth required. It's not a lot of it, but when it's there, it's really important. And there's a back-end network where the nodes are exchanging elements of data, and that's very bandwidth intensive on the networking infrastructure. So if you look at the traditional way that this has been solved by a lot of different systems, you take your node, whatever sort of server building block you're using, and we need redundancy on a lot of these networks. So you've got a couple of ports up to the back end switches. You've got a couple of ports connecting into the front end network, and you've got realistically, you'd have a couple of management ports as well. You might even have some IPMI, kind of true server management ports in there that aren't even shown here. It's a lot. And that works okay when you're a small scale system. But if the whole point of this is to scale out, it quickly gets really, really complex. And one way to see this is to walk into a data center that has a scale out storage system, and you see pictures that, or you see things that can look like this. Now, we can argue there's some cable management that could be improved in this particular system, but it's an indicator of it's a symptom really of how complex some of the networking architectures have been. And so what we said back at Storage Field Day 10, 5 years ago, and this is literally a screenshot of the slide we presented, was we aim to tackle this by integrating the networking that exists in a lot of these systems into the product. So into our system, we are putting two, we call them fabric modules. They're basically network switches. So we're using standard merchant silicon. This iteration used Broadcom Trident 2 switch ASICs. And really the way we think about this design is that it's taking those three networks, the front end network, the back end network, the control network, and it's collapsing them down onto a single high performance fabric, right? The SerDes, the links are certainly capable of supporting all the traffic. What we needed and what the industry needed was all the software defined networking capabilities that are built into the modern switch silicon, and we take advantage of that. And so in some senses, we're not doing anything super exotic if you come from a networking background. But if you look at our product as a whole, it's one part storage, one part server building block, one part networking, and we've really integrated all of that together. And our thesis from the beginning was that this integration was going to simplify what it meant to deploy large-scale systems. And that's really proven out very well for us in the market. So if you look at where we are today, it's that same architecture is sitting directly inside of the product. We can scale from, on the small end, a 7-blade system that has those two fabric modules in the rear of the chassis, 7 blades plugged in the front. The smaller blade size is a 17 terabyte blade. And we can non-disruptively, elastically scale that out to 150 blades. We can take it to 52 terabyte blade sizes. When we go to multiple chassis, we scale out with a pair of, we call them external fabric modules that you can see at the top that pull all the networking elements together. So there are some cables that have to go, but you can see that's a production deployment on the right that looks a bit like the demo or the lab system I showed in the earlier segment, where this is a 75 blade system. You can get several petabytes worth of capacity. It's about a half a rack worth of deployment. Very simple. We've tried to minimize the number of fans that spin and the number of cables that wiggle, because now that we've removed all the disk, those are the mechanical components that are still most likely to fail in a data center. And so we're really, really happy with the decision that we made to internalize the networking, as it's helped our customers be able to stand up new deployments in hours rather than days or weeks and get up and running really, really easily. So let's dig a little deeper though into the tech. How does this work? And so this cartoon architecture diagram really represents how we think about the system in its internals, especially from how we handle the networking and load balancing. So each of the kind of columns here represents some of the hardware, and I'll talk through some of the logic of what's happening on each blade. So there's compute, memory, and then we have the flash and non-volatile memory that we have in each blade. And those are connected together into this redundant high-performance network fabric. And so from a networking point of view, we're using all standard technology. We use link aggregation groups or port channels to bundle multiple connections together, we set up a high availability pair, so everything is redundant at the networking layer in case things, they're to be able to tolerate component failures. And we're taking advantage of features that exist in switch silicon to virtualize all the IPs. So when a customer deploys a 75 or 150 blade system in their environment, they should never have to go to their networking team and say, I need 175 IP addresses in this block, right? This should be configurable with just a handful of IPs, some for a management network, virtual management network, some for a data network, but be really, really simple to get up and running. Something that a storage team can do with minimal support from other groups in an organization. And so to do that, we're doing things like rewriting the network endpoint addresses to get a virtual IP, to be able to support we can virtualize, we can create different subnets, you can create multiple virtual IPs all through the management UI if you want to segment traffic in different ways. So all of this is supported using a lot of our standard off-the-shelf networking hardware that we've built into our, we've built into our product, and we've written the software to take advantage of it. But it also, the work to scale and to hit the load balancing capabilities to deliver that all the way through the stack, it extends far into our software. This isn't something we can just solve at the networking layer. So we do load balancing of connections across all the blades. We have the system, and I'll talk in more detail about how the internals of our software work to handle this, but each blade in the system can service any client connection or any protocol. The logic and handling there is all designed to be stateless. Now, obviously we're a storage system, so there's some state somewhere, and I'll talk through how that all works, but the logic can actually be run anywhere. So we can actually move logic if there are component failures, if a blade gets pulled or removed. We can rebalance connections. We can still access all the file and object data that exists on the system. And each blade is capable of restarting any given connection, and we have integrated that all the way through into the protocol stack as needed to serve connection handling requirements as dictated by various file and object protocols. So there's a lot of the different pieces of the product that all come together to achieve this end simplicity result where we can get to 4 or 5 petabytes. And with data reduction, we have customers that are up at the 8, 10 petabytes in a single namespace at this point. And if you look at our trajectory over time, we just continue to scale the product every year or so as we've gone through new hardware revs, new scale revs to get bigger and bigger. And we see that continuing well into the future as the architecture we set out has kept up very well with technology trends at the media level.
Brian, I have a question. So you didn't mention the flash memory part. I mean, we are in a transition, industry speaking, from TLC to QLC. So at the moment you have QLC on other products, but not on this one. So what will happen when you will have, this massive amount of flash memory capacity available to this system, but with all the, problems of QLC? I mean, all the,
Yep. Absolutely. So that's a great question. And I'll go back in time. The first versions of FlashBlade actually shipped with an 8 terabyte blade with MLC flash, right? As that was at the time the right technology for us in 2015 when we were developing that, in 2016 when we launched. We've actually shipped 6 distinct different flash technologies. So these are multiple vendors, multiple revs. We're shipping in high scale production today with TLC on FlashBlade. We have a really healthy roadmap. I'm not going to go into details of where that goes, but we've got a clear view into where the technology is going to head. And the answer to your question about, how will we continue to scale as the media gets denser, effectively, like how does that work? And this goes back to one of the fundamental bets that we made in this product architecture, was that by having direct visibility into the flash and co-designing the, how we're structuring the media, we've branded this as direct flash as the technology, but we've really co-designed that with a database layer, and ultimately a file system and object storage layer above that, we now have so many new degrees of freedom to be able to solve the challenges of scale. So for example, you have, any modern, any flash system, a flash-based system has to do garbage collection. We have the compute resources as well as the visibility into a entire file system and object storage stack to understand recency of data use, frequency of data use, and make intelligent decisions about how to rewrite data segments and do the mechanics of garbage collection at scale. And so these are, the original bets that we made have played out extremely well for us as we've kept up with the media technology, and we don't see any end in sight for that. And we have every intention of continuing to ride the technology curve that allows us to build, bigger, denser systems for, the next decade, basically.
But we had the 8 terabyte blade for a short amount of time. Now you have a massive installed base with these new blades. So will you manage a sort of, dynamic balancing between the blades, tiering or something? Is it too early to talk about it, or,
That, it's like you read my mind. Let's actually show you what we're doing a bit with the customer. I'll come back to there are other variations of, I think, what you're asking about, but let's look at a specific customer and the journey that they've been on, because it gets exactly to this question a bit. We have a customer in Korea that was building, back in 2017, they were building a deep learning platform for their internal users, and they started with a smaller system. So at the time, we had recently introduced the 17 terabyte blade. So they got started with a 9 by 17 terabyte system. As their platform took off internally, they expanded. And so they went from 9 blades to 12, right? So that's one of the things this architecture has enabled, is pretty incremental elastic scaling as a customer's needs and budget allow. And they then migrated, as they saw where they could calibrate and see where their platform was going, they realized they needed more capacity. And they were getting plenty of performance. They needed more capacity. So we online, non-disruptively migrated them to 52 terabyte blades. So this is one example, and we've been doing this with a lot of our install base that may have started with 8 terabyte blades or started with 17 terabyte blades, is being able to go in and non-disruptively expand them to the higher capacity systems if that's where their needs are. We do support operations. So to another part of your question, we do support operations with mixed blade configurations, but it's not optimal. And the reason for that is we are forming erasure encoding stripes. And if you have an 8 terabyte blade and 14 52 terabyte blades, we can't somehow make that 8 terabyte blade act like a 52 terabyte blade from a redundancy point of view. And so we recommend that as an intermediate transition point. And really, what we found is that customers aren't necessarily looking to operate in a long-term mixed mode like that. They see where their data requirements are going, and what they really need from us is non-disruptive evolution towards the larger scaling outcome. And this is just one example of many that we've done, some smaller expansions, obviously, and some really bigger than this, to go from what was originally 8 terabyte blades to 75 by 52 and, multiple deployments at a customer and so forth. So there's, in the real world, we see a lot of different needs, but this has been probably the most common pattern of how to scale a platform like this. And we expect this to continue. So this customer in particular, you can see, they're driving a fairly high read throughput workload for, their particular cluster. But from 2017 to today, they've gotten 6x more performance by expanding their blade count. They've grown, it's actually more than 16x in capacity because the rate efficiencies got better as they scaled out. They've done, at least 8 discrete software releases, all non-disruptive expansion that we do, or non-disruptive upgrades that we do in the platform. And so this is, one concrete example just to try to emphasize this point, which is really important to us. And it's not easy to, hit non-disruptive expansion like this. It's quite a lot of engineering work to make sure, and testing work to make sure that we can do this. And we did this with the FlashArray M series on our other product line, where we've we can change out entire hardware. And John Colgrove, Pure's co-founder and CTO, he talks all the time with our engineering teams of the storage system should live for decades, right? A single storage system should live for decades, no forklifts. The hardware will all be different, and it's our job to make that non-disruptive. And that's really, you can see how that plays out. That's a big deal for customers in practice. And you can see how that plays out here for us.